The path of a particle moving in the plane may not be the graph of a function, and in that case we cannot express y directly as a formula in x or x directly in terms of y. Instead of this, we need to use a third variable t to describe the path, and this t is called a parameter, and the points on the curve are given by x is some function of t and y is some function of t. And of course it's very natural to think of t as time here, and the position of a particle at time t requires two coordinates to describe it, and it also varies as time varies. So given equations such as these describing a path, the set of points xy equals ft(g) of t for all t in some interval I form a curve, and that curve is called a parametric curve. The two equations, x equals f of t, y equals g of t, are called the parametric equations of the curve. As mentioned above, often t represents time, and we can think of xy equals f of t, g of t as the position of a particle at time t. If the interval upon which I'm plotting this curve is of the form a less than or equal to t, which is less than or equal to b, then the point f of a, g of a is the initial point, and the point f of b, g of b is called the terminal point for fairly obvious reasons. Well, let's draw and identify the nature of the parametric curve given by these two equations. The x-coordinate for any given t is cosine of t, and the y-coordinate for any given value of t is sine of t. And we're allowing the t to run from 0 to 2 pi. So let's start with the initial point when t equals 0. This gives me a value of x equals cosine of 0, which is 1, and a value of y equals sine of 0, which is 1. So therefore the initial point on this curve, the starting point for my graph of this curve, is the point 1, 0. And when t increases to pi over 4, the x value is now 1 over the square root of 2, and the y value is 1 over the square root of 2. Again, if t increases to pi over 2, the x value becomes cosine pi over 2, which is 0, and the y value is sine pi over 2, which is 1. Likewise, when t is 3 pi over 4, the corresponding point on the curve is minus 1 over the square root of 2, 1 over the square root of 2, and so on. When I get to the terminal point on the curve when t is 2 pi, then the corresponding point is x equals 1, y equals 0, which coincides with the initial point on the curve. We can plot these points, and we see that they all lie on a circle. The initial point is here at 1, 0, and when t is pi over 4, we get this point 1 over the square root of 2, 1 over the square root of 2. When t is pi over 2, we get the point 0, 1, etc. And as we increase the angle, we move right around this circle of radius 1, with the terminal point coinciding with the initial point at 1, 0. So filling in the details for the angles in between the ones we've chosen, we see that as t increases from 0 to 2 pi, the points trace out a circle of radius 1, moving in an anti-clockwise direction from the initial point at 1, 0 to the terminal point at 1, 0, which coincides with the initial point. So we have an animation of the graph here as we trace out this curve. We start at the initial point 1, 0, and as t increases from 0 to 2 pi, we move around the circle in an anti-clockwise direction until the terminal point when t equals 2 pi, we get right back to the initial point again.